So when we are talking about image enhancement, we mean resolution enhancement. We may mean illumination enhancement, and we may mean denoising or restoration. We will talk about each of these steps. If you notice, we already have talked about the first one. This one we talked about interpolation. Interpolation is one way of enhancing the resolution. We understood that, can you please close all your laptops? We understand that by interpolation we have something which is called blurring effect. We didn't like it. Later we will get back, while we are talking about image enhancement, we will get back how we can enhance this image even better. We will focus quite a lot on illumination enhancement. Today and next week we will talk about the techniques that we have in order to enhance the illumination. We will have one exam question about that one. And then we also talk a bit about denoising. We will try to see that how we can use some conventional techniques, conventional methods in order to remove some well-known noises that we have inside an image. So when we say image enhancement, we basically mean these three steps. We see that, I mean, some of these things that I write here, we have it already in the slides. We see that in general, for the image enhancement, we can do it in two forms. And these two forms is this. We can do it in the spatial domain. A spatial domain is like in 1D we have time domain. In 2D we call it a spatial domain. In other words, it means that I give you the image, you will do something on the image. So all your technique is on the image that I give you. You do not take this image somewhere else to do the process. Now, if you are doing it in the spatial domain, we understand that there are actually two ways of doing it. Either you can do it pixel by pixel. In other words, you look at one specific pixel and you do some operation on that pixel. Or you can look at it as, let's say, well, you can do it as a whole image, or you can do it as let's say section or region, or I don't know, we call it a kernel by kernel, segment by segment, a macro by macro. So you will see sets of the points, and by looking at those sets, you decide what you need to do. Another way of doing it is doing it in frequency domain. Now, one way of enhancing this image is actually I give you the image, you take the image to another domain for some reasons, and you do your process in another domain. And when it is done, you have to transfer it back to a spatial domain, because we can see the images through the spatial domain. So this one we understand that we need to do a transformation and inverse of that transformation. So we are introducing a new complexity into our system, but sometimes it is the only way that we have, and we have to agree with it. So in this course we will talk about both of them. We start with the spatial domain because it's easier. We don't need to talk about how we want to transform an image from one domain to another domain. So image enhancement. And the definition for image enhancement, what is the definition? What do you think when you hear the word image enhancement? What is the enhancement means? Improvement. We want to make the image to look better. Why do we want the image to look better? Apart from we want to put it in the Facebook, but why do we want to have an image to be a better resolution, better lightening, noise-free?
Makes it easier to process it.
Yes, if you make it easier to process it. Especially if we continue to the computer vision, it will make it easier to extract features. Not only make it easier, but it makes the feature that they extract to be more meaningful. In other words, you do not extract the noises because you can define the way that you want to extract, and if there is noisy image, you extract the noises and you misinterpret them. Right? You have noise, and then your program detects that you have 4 eyes on this face. So we try to remove the noise, so it will be working in a very good form. As I said, we have 2 ways of enhancing an image. We can do in these 2 ways. One is we are using a spatial domain. In time domain, you don't need to transfer it to any other domain. The other one is converting it to the frequency domain. And in order to convert the frequency domain, if you have taken the signal and system course or signal processing course, you understand that in order to do it, we use something which is called Fourier transform. And when the time comes, I will talk about the formulation, and we will see how we can convert from a spatial domain to frequency domain. Now, and the operation, as I said, we can have 2 ways of doing this operation. One of the operation is directly happening on the pixels. So we have a pixel, we have an image, and the image has made of lots of pixels. So we do the work on this pixel. In general, I don't know why we don't have a laser pointer in here. And this is very sad. And none of you has a laser pointer, right? I don't know. When I was a student, we used to have one in our club. Anyway, I need to move on. So what happens with this pixel by pixel transformation is we are introducing a new function. We are introducing a new function, and this new function has an input argument and has an output argument. What is the input argument? The current value of the pixel. And what is the output argument? The new or calculated value of pixel for the image. So the thing is that I give f, which is an image which is not with a good resolution, or is not with a good illumination, or is noisy, and I am hoping that this t, this transform function, this function that we have, this transformation that we have, converted into an image which is addressing all those enhancement properties. Now, in order to do it, we said some of the operation is pixel-wise operation. In other words, you don't care what is the previous pixel, what is the after or the next pixel, what is the up or the bottom pixels. So you look at the current pixel value, you do some calculation, and you calculate the new pixel value and you place it in there. But sometimes we need to have something which is called a neighborhood. Now, in order to know what is a neighborhood, we need to define a mask, as you see it in here. And a 3x3 neighborhood means the center of the mask that you have is your interest point of interest. What is the meaning of point of interest? It means that the output that you calculate should be placed in here, in the new image. And in order to calculate it, I look at the whole neighborhood. So, if I want to find the new value for pixel row 5, column 10, then it means that I put this neighborhood, this mask that you have, in a way that the center is on row 5 and column 10. Now, if this is the index x and y, what we need to know is this. This one is x minus 1 and y. This one is x plus 1 and y.
No, sorry, x and...
Correct, that's correct. Yeah, it's okay. That's correct.
This one is x, y minus 1, and this one is x and y plus 1. And similarly, what is this? x plus 1, y plus 1. And what is this? X minus 1, y minus 1, and the rest you can guess it. Why we need it? Because later when we are talking about developing a formula, we need this type of representation. So in general, what we have two ways of doing the process. We either do it on a single pixel, I don't look at the neighbor, it's called pixel processing. The other one, I will look at a neighborhood. I have a mask of 3 by 3, 5 by 5, 7 by 7, or whatever it is, and I look at the whole value and I do the tasks. There are a few terms that you need to know. One term is mask. Now, I had this 3 by 3. This is called the mask. Another word for that is kernel. I also call this one a 3 by 3 kernel. There are synonyms. Or I call it filter. It's a 3 by 3 filter. Or I call it a neighborhood. Okay? So these are all synonyms. In the book, if you see the Gonzalez book, they usually write it mask / filter, and at some point they use the word kernel. In different books they use different wording, but we understand all of them are the same thing. Now, in this course, when we are talking about some operations, what happens is we will tell you that in order to do, let's say, this type of filtering, you should have a mask whose value is known. So there exists some mask with the known coefficients, known values, which you need to know them. I mean, in the exam you have them in your book because it's an open book exam, but you need to know them in general. Some of the masks, they don't have any weight, and we just place it on the image and we look at the current value of the pixels. Okay? And we do examples on that one in a few minutes when the time comes. And the first thing that we hear in today's lecture regarding to image enhancement is contrast enhancement. So let's see, what is a contrast enhancement? So one of the things on image enhancement was illumination enhancement. But what is illumination? What is illumination? Abdullah, what is illumination? I didn't hear you. Lightening of the image. Is it true? Well, I can tell you that it's partially true. Illumination consists of two important things. What are they? There are two terms. That is true, but you are giving the definition of one of them. One of them is, I think you have it here. It's called contrast. The other one, Abdulaziz gave the definition of that, and it is called brightness. It's called brightness. Let me go to the module, and I want to show some sample images that we have for different combinations of this. Now, I want to show an example of each of these ones. But before I show the examples, what are the conditions regarding to the brightness? We have either bright or dark image, right? Yes. For the contrast, we can have a high or low contrast. So how many combinations do we have? We have 4 combinations. And of course we have the ideal image, but this ideal image, we don't talk about it, I will tell you in a few seconds. So, first thing is we have to talk about bright image, which is, let's say, high contrast. Then we will talk about a bright image, which is low contrast. Then we will talk about the dark image, which is high contrast. Then we talk about the dark image, which is low contrast. And then, after I show an image, I will tell you that what we mean by brightness and what we mean by contrast. Now, we know this lovely image of obelix, right? Now, obelix, which is dark, I cannot go to the next one. Obelix, which is dark, looks like this. So this is a dark image. And an obelix, which is bright, looks like this. Is there anyone who is not understanding the difference between a dark and a bright image? In other words, if I give you these 2 images side by side, so if I give you these 2 images side by side, is there anyone, but don't shy, is there anyone who looks at this and says that, when I look at these 2, I consider this one to be a bright image? So we all agree that when we look at these 2, we say that this is the dark image and this one is a bright image, right? Please remember, brightness, darkness, low contrast, high contrast are relative. If I show you an image and I tell you if it is it a bright image or a dark image, you really cannot say, I mean, as a human we say, oh, it's a dark image. Why? Because in my life I have seen zillions of images and my brain automatically compare it, and on an average this looks like to be a bright image or this looks like to be a dark image. But in order to have a very, let's say, healthy decision, we need to have 2 images and we say comparatively, this is a dark image or this is a warm image. A bright image. It is like the temperature. I tell you that 10 degrees. Now, 10 degrees, is it cold degree or is it a warm degree? You have to say that, okay, yesterday it was 5 and now it is 10. So, 10 degrees is warm. Now, yesterday it was 20 and now it is 10. So, it is cold. I mean, I have been in Cyprus. In Cyprus in winter it gets 4 degrees and people have lots of thick things to wear to say that because it's very cold. And in Estonia, when it is 4 degrees, you go to swim in the river. So you understand that this is very relative because you have to look at how it goes within an environment. The same thing is valid regarding to this brightness and darkness. So you can say that the one on the left is dark because you see the one on the right. And you can see the one on the right is bright because you can see the one on the left. We will come up with a better definition a bit later when we are talking about bright or dark image. Now, let's look at the high contrast image and a low contrast image. So the image on the left is a low contrast image, and the image on the right is a high contrast image. Is there anyone who knows what is a contrast? Yes, because you are the one who defined it actually. Yes?
It's the difference or the range between the...
It's range. It's the range, shows the range of the colors, or let's say intensities. I show you a color image, but it can be grayscale. The range of the intensities. So we say that here in the left one we have the range which is, let's say, 50, and the one in the up we have a range which is, let's say, 250. So 250 is bigger than 50, so we say that this one is higher contrast, this one is lower contrast. Okay? So we look at the range in order to find out if it is a high contrast or low contrast. Of course, range is not a very good variable to look. I will tell you what we really look. But in general, you look at the range and estimate that this is a low contrast or this is a high contrast. Ri, as a human, we would love to have which contrast? High contrast. We like high contrast. High contrast is always better. That's why that 90% of the filters in Instagram are actually high contrast. They try to make the image high contrast. Okay? But not necessarily one artist can come out and say, oh, such a beautiful image. It's very low contrast. Okay? So we have low contrast, high contrast, bright and dark, so we can make in general a 4 different combination of all of them. Now let's see how we can see if an image is low contrast or high contrast or bright or dark. An image, which means it is an unsigned 8-bit image. I show you a color image, but we consider it as a grayscale image when I'm talking. It has a value between 0 to 255, right? So a pixel eye has a value between 0 and 255. And the mid value is 128, right? If I give you lots of data, how can you see how the data have been distributed? In the statistics, what was the visual tool that they could use in order to see how they have been distributed? Histogram. So if I give you lots of data, in order to see how they have been distributed, we look at the histogram of those data. We do the same thing with the image, because for us, it's bunch of numbers, which are between 0 to 255. So we look at the histogram of an image. How we look at it, how we calculate it, we will learn. You might know it, but we assume you don't know it and we learn. But let's say for the time being, we know what is the histogram of an image look like. So, this is the histogram of my image, and we know that the histogram is lots of bars, so it is discrete, but I will just connect the top of these bars in order to have a continuous form. So I will have, let's say, a graph like this. Okay? Now, when I have a distribution like that, there are two very important parameters which are describing the characteristics of this distribution. What are those two, Martin? Martin? You have only one Martin in this class, you know that? It's too complicated. Much simpler. Two very simple parameters that we always use for describing a distribution. Once? Tell me the term of the parameters. Everybody know about it, I know. Larry? Mean and variance. The standard deviation is a square root. We don't like a square root. Let's say variance. But let's say mean. I mean, what Martin said is also valid. I mean, a square root or I don't know, area under here. They are all important parameters. But the simplest ones are mean and let's say variance or a standard deviation, which is a square root of the variance. If we have the mean, actually by looking at the mean, we can find out whether the image is bright or dark. In other words, by using the mean, I can always discuss about the brightness of the image. How? 0 is representing which color? Black. And 255, what's her name?
Crystal.
Krister.
No. Crystals.
Chris.
Yeah,
Good. Chris, what is the 255 representing?
White.
White. So, and white means very bright, the brightest thing that you can get, and 0 is very dark, the darkest, black, the darkest thing that you can get. So if my mean is closer towards the 0 Ozan, what can we understand? It's going to be a dark image. And again, if the mu is towards the 255,
it will be brighter.
It's going to be brighter. And we know the mean is 128. I mean, I said that we have bright low contrast, bright high contrast, dark low contrast, dark high contrast, and we have in my another hand, I said that we have the ideal image, but we don't talk about it. We said 128 is the middle point, and we can say that if you are at 128, we cannot say that it's bright and dark, we can say it's good. But this is a very, very subjective thing. In other words, you can look at an image and say that, oh, actually this is not a bright image or not a dark image, it's a very normal image. And we have to respect that opinion. In other words, there is no actual definition to say that what is ideal illumination. Based on different application, we can have different type of lightning to be the best ideal one, right? Some people may say that, well, actually, if the mean is between 120 and 100 and let's say 35, this is a range which is always ideal. So you can come up with a range. So you have to look at your application in order to find it out. Maybe you have a picture from the sky, from the galaxies, and we know that the majority of things are black, so we are expected to have the mean to be close to 0. So your ideal image might happen to have the mean to be, let's say, 50 or 60. So you have to look at your application. Well, in general, if the mu is less than 128, the tendency is towards dark, and if the mu is greater than 128, the tendency is towards bright. So if I look at the mu, I can have some general taste that the image that I'm looking, it should be a bright image, or it seems to be a bright image. So these things, it seems to. In other words, someone can come on and say that, no way, this is a dark image, although the mu is let's say 140. But we can use mu in order to come with a solid decision. And the solid decision is this. Let's call I to be image before enhancement, and I hat to be image after enhancement. Okay? If mu I is greater than mu I hat, it means the enhanced image is becoming darker. Now, look, an image is becoming darker does not mean the image is dark. Maybe the average is 250, and after enhancement it will become 190. So still both are categorized in the bright side, but when you compare these two, the one which has lower mean is darker than the one which is in the upper mean. In the exam, the question that I typically ask is you need to calculate the mean and you need to comment the mean before and after. In other words, you say that one of the means is greater, so it means that one is brighter. In other words, I do not ask a question which is subjective, and you can say this is bright and you can say this is dark, and both of them are correct. But what happens is that if someone says that I hat is becoming brighter, this is definitely wrong. Because we understand that its mean is less than mu I, so definitely it will become darker than the original image. And obviously, if mu I is less than mu I hat, it means the enhanced image is becoming brighter. Sometimes the image is dark, and we want to make it brighter so we can see more details. Remember, when we are enhancing the illumination, we are not creating extra information. What happens is that maybe because the contrast is very small, the difference between the pixels is too close to each other, which our eyes cannot see. In other words, the pixel 1 and pixel 0 and pixel 5 from our eyes are all the same black, but they are different tones. Now, for us, in order to see it, imagine I have 0, 1, and 5. In order to see that there are 3 values, if I say 0 is 0, 1 is 128, and 5 is 250, then I can easily see the 3 tones. So what we try to do is we try to put the distance between these pixels as much as it is possible so it is visible. So we are not creating new things. Maybe you don't see it in the original image, and after enhancing it, you see the background and there are lots of details in there. You are not creating it. This is something very important. In the interpolation, we are approximating, we are guessing, we are estimating. So there are lots of values that we are creating. They are not real values, we are creating them, so there is a probability of error. But when you are doing the illumination enhancement, we do not create anything. If it exists, we just make it more visible. And we have the potential of actually killing the values. How do we kill the value? Yes, maybe you make it big. You make it that much big that lots of values go above 255, which means that we are making it 255. So we lose lots of data. If we lose them, can we get them back? No, they are gone forever. If we make it much bigger than 255, in other words, I start to make the illumination high, and after some point I will see lots of bright parts, and lots of details are lost, and then it's called wash out. I'm washing out the image. This is artistic. In Photoshop, we have the wash out filter, so some people may like it, may enjoy doing it. So we can have the wash out, which means that there are some details I kill them, but we never create an information, or we never create any details by using this. So if I look at the mean, I can come up with the brightness. So we said we are talking about the mean and the variance. So I'm sure that you can guess that the variance is telling us about the contrast. The variance, or standard deviation, is telling us about the contrast. If the distribution is something like this, then it means that we are dealing, the majority of the pixels are very close to mean, so we are not changing too much, although maybe the range is big enough. Then we call this one to be a low contrast image, especially when we are comparing it with such an image, which my drawings are awful, but when you compare the blue and the black one, we understand that the black one, although maybe they have the same range, but the black ones, the probability of having pixels which are further away from mean is higher. So this one is called higher contrast compared to this one. Again, in mean, at least we could define the 128 to say that, okay, less than 128 dark, greater than 128 bright. But for this one, for variance, we cannot really define anything. You do need to have two variances in order to say one is high contrast, one is low contrast. If we calculate the variance of these two, we will see that the variance of the one on the left is much lower than the variance of the image that we have on the right. Then you look at the variance and say that, okay, this one is higher contrast than the other one. And now this is something which is quantitative. It's not subjective to you to say that, oh, this one is low contrast, this one is high contrast. Maybe both of them you can categorize it as a high contrast, I don't care. But what I care is this image, because its sigma is greater than this image, so this one has higher contrast with respect to this. This is something that in the exam definitely you'll be facing. You need to calculate the variance or mean, and then you need to compare what happens before and after enhancement. So it's pretty simple. You have to simply compare the values. Okay, we are still on slide 6. So We said on the illumination we have the brightness and we have the contrast, because when we use the word illumination we mean both of them. So if I tell you that I have an illumination enhancement technique, then you usually should ask, if you are proficient on that, do you enhance the brightness or do you enhance the contrast, or do you enhance both of them? Usually most of the illumination enhancement techniques that we have are actually contrast extraction. Why we are focusing on contrast extraction more than the illumination enhancement? What is the contrast from physical point of view?
Details.
Well, contrasts are resulting to details, because the contrast, as you can see, is the difference in the visual properties which makes us to be able to see an object. To say that, okay, there is a border for Andreas, and this is a border for Chris and his glasses, and so on. Okay? So the contrast will help us to do it. Apparently, our eyes, the visual system, is sensitive to the contrast change than to the brightness change. So we can slightly change the brightness. If you don't affect on the contrast, you don't understand it. And we are all alright. We have a problem when it comes to matter of the contrast. That's why that we pay lots of attention in order to make the contrast better and enhancing the contrast. And as Egil says, because based on the definition of the contrast, all those details, edges, we can distract them, we can extract them if we have a good contrast image. So what we want to do, we want to extract the contrast. Now, here you can see an image, a histogram of an image which has a low contrast. And what we try to do, we try to make the contrast higher. And usually, in order to make the contrast higher, we want to see that what is the minimum value that I can represent, which is 0. What is the maximum value that I can represent? 2 to the power n minus 1, depends on number of bits. In our case, it's 255. With high probability in the exam, I am asking you for a 3 or 4 bit image, so you can do the calculation easier. So it's either 7 or 15. So we try to make sure that all the pixels start from 0 and they go to the maximum number. So we have whole numbers. So the probability of having everything is possible. It's not a probability 0. Now, how we do it? We have lots of formulas, we have lots of transformations which we can use it. And today we will start to talk about some of these transformations, and on next session we will continue with more complicated transformations in order to enhance or express the contrast. And as a consequence, you see that this is a grayscale image which has a low contrast, and after enhancing it we will get a higher contrast. In order to do it, we said that this is